let's have a look at our temperature scales. And so there are three main temperature scales. You are probably familiar with the Fahrenheit scale that we use here. And of course, just orient yourself. So water freezes at 32 degrees Celsius. Water boils at 212. And so let's look at our other temperature systems. And so I'm going to look at Celsius. And so Celsius, they decided to kind of set it more evenly. And we can see, right, water freezes at 0, water boils at 100. A lot easier to remember. And then now we have our Kelvin. So let's compare those. And so Kelvin is based off of this concept of absolute zero. And absolute zero is defined as the complete absence of motions. And so this is a theoretical temperature. They've gotten pretty close, I want to say like to 0.4 Kelvin or so. And right, you have to think about what this means by the absence of motion. So this is absence of any sort of molecular motion. I'll add that molecular motion. And so we would have to imagine, right, even our electrons would stop moving at absolute zero. And the Kelvin scale was set with our Celsius such that 1 degree increase in Celsius is also equal to 1 degree increase in Kelvin. And you can see that that there is a 100 temperature difference between water boiling and water freezing. Down here we have our formulas. So again, I would not expect you to memorize any of these. Just go ahead and write them down somewhere. And then you may notice small differences in formulas if you look at other resources, and that's only because, so if you do like 9 over 5, that's 1.8. So you might see this number 1.8 times our temperature in Celsius plus 32 there. And then, of course, if you want to go from Fahrenheit to Celsius, the significance here is, of course, you have to do the subtraction first and then multiply by 5/9. And so this is the common conversion factor. I just want to point out a few issues you may have encountered. And so commonly we just say, okay, the temperature Kelvin is equal to our temperature Celsius plus 273. Except if you did the homework, you notice that it might have used this more specific factor of 273.15. So that is indeed the more accurate value. But most of the time, we only report our temperature right to the ones place most accurately. And the only case where it became an issue was where the homework uses wording of exact. And so I think it was convert. I'd have to look at the homework with something of convert. Let's see if I can find it. I have the homework here. Yes. Convert the freezing point of water, and it puts 0 degrees Celsius exactly. And it was only because it used this exactly term that the answer key kind of called for this 273.15. Otherwise, right, it wouldn't really matter. Other calculations that you're going to encounter in our homework is just a density calculation. And so in your homework, you have this sort of grams per milliliter, just practice problem. And so density is just defined as any mass to volume ratio. So we will commonly see this gram per milliliter. But that being said, right, we could have kilograms per liter, pounds per gallon, right? Any other sort of mass to volume ratio. And so then we have our formula. So again, density equals mass over volume. And I often tell people about this triangle trick if you haven't seen it. So again, density equals mass over volume. Mass goes on top. Density, volume. This is a quick little algebra trick in case you want to just double check your algebra sanity. And so whichever property you're solving for, you can just cover it up and it tells you what to do. So again, if you're wanted to solve for density, you cover density. We're left with mass over volume. If you wanted to solve for mass, cover mass. You're left with density times volume. And so now let's just look at this quick definition. And so the reason why we want to talk about density is because it is an intensive property. So meaning it does not depend on the amount. So this would be a property inherent and does not depend on amount. And so density is again one of those examples that helps us to identify substances so we can figure out the density of unknown metals, and that would be helpful. Other intensive properties would be melting point, boiling points. Again, right, those will not change. Reactivity, we won't go down the full list, but then we just want to compare that to an extensive property, which would be amount dependent. And so that would be like mass and volume. So the things that may make up density, but right, you can always find that ratio, give you your intensive property. So mass, volume, length, right? Anything that dictates amount. All right, so try this problem. Determine the volume of an object that has a mass of 455.6 grams and a density of 19.3 grams per centimeter cubed. I would advise you pause here and just so you know, a centimeter cubed is a milliliter. So for this, there's two different ways to approach it. Again, we can go back to our little triangle trick, density, mass, volume. Or we could think about our unit canceling. And so again, right, what we really have is 19.3 grams per milliliter. We want to get volume here. And so now we're kind of seeing our units. So 455.6 grams. Now we need milliliters on top. So suggesting I might want to divide by 19. Double checking with our triangle trick. So yes, we're given mass divided by volume, or excuse me, mass divided by density gives us volume. If we, again, cover our triangle here, cover our little volume on our triangle, that's what we're solving for, mass over density. So now we do that. And we're given 23.6, so D here for our answer. Our last little bit here is we want to bring in this terminology, specific gravity. And your book has a very narrow definition of it. So actually, specific gravity is usually just any comparison of densities, but your book makes it more specifically of a comparison of a density to water. That being said, the density of water is 1 gram per milliliter. So if you divide any density by the density of water, right, you just essentially end up canceling out the units. That makes sense to people. And so we can look at a quick example here. And so looking at the density of hexane, it has a density of 0.66 grams per milliliter. So if you take the specific gravity of that, again, you're just dividing by 1. So we're just canceling out our units, leaving us with 0.66 for its specific gravity. Again, especially according to our narrow textbook definition. So again, if you were to look at other sources comparing other things, this could just be a general ratio of one substance to another.